Our next speaker is a phenomenon. He really needs no introduction. I was very lucky to have Michael Atiyah when I was a student at Cambridge. He was a new lecturer at the university. He's revolutionized mathematics in the 1960s, unifying analysis, topology, and geometry. The Atiyah-Singer index theorem is known by every student of mathematics. He's been professor at Oxford, at the Institute for Advanced Study, at Cambridge. I don't know where else. He was Master of Trinity College, Cambridge, President of the Royal Society, received the Fields Medal for his work in mathematics, I believe in 1966, and lives now in Edinburgh with his charming wife, but I couldn't say he's retired because I can't imagine Michael Atiyah being retired. Michael Atiyah, Sir Michael Atiyah.
I see. Right. Okay. Well, I'm very pleased to be here at this big occasion of the Clay Institute meeting and to help to launch the problems for the next century. I'm very pleased to see so many young people here in the audience. Of course, I'm very pleased to see old friends as well, but I'm particularly pleased to see young people because this occasion, which is really the handover from the last century to the new century. We are here to really summarize the state of mathematics at the end of one century and to describe the problems for the young people to work on in the new century. So this is really a message to the young people. This is your problems. You are the ones to whom we look for solutions of these problems. Now, the four problems I've been given, I explained, in case you didn't know, that the Clay Institute chose the problems. We are simply mouthpieces. At least I am. And I've been asked to talk about four problems. The problems are very varied, cover a wide range of fields, but I have tried, I'm not going to go into too much technical detail. That was not my task. The task is to try to put the problems in some kind of context, and I would like to, as far as possible, unify them by some common themes, to emphasize that although we identify many individual problems in mathematics, mathematics does have an overall unity, and the unity is very important, as well as the diversity. So the four problems will all be on the frontier between geometry and analysis. And geometry is very closely related to physics, and analysis will, of course, enclose other parts of mathematics, such as algebra. But it's that geometry-analysis interface that underlies all of them. Now, in the 100 years between 1900 and the year 2000, one of the themes one can see in the development of that mathematics, that century, was the shift between, for example, linear to nonlinear. Linear theories were gradually understood, and the shift has been more towards nonlinear theories. There is also a similar shift in the dimensions. Geometry and analysis in dimensions 1 and 2 is well understood. We've moved on to 3 and 4 and sometimes higher. This shift in dimension is one of the phenomena that took place in that century. All the problems I'm going to be concerned with are really centered around, in one form or another, partial differential equations. Now, partial differential equations come in many forms. You start off first with the linear equations with constant coefficients, which you understand by Fourier transforms. Then you go on to study linear equations with variable coefficients, or what is more or less the same thing, linear equations on a curved background space. And then from there, you can start looking at quasi-linear equations where the linearity is sort of weak in some sense, then to the more fully nonlinear ones. Nonlinear is not a property, it's the absence of a property. So you can infinitely many subdivisions of nonlinearity, of course. And behind all the analysis of these questions, there is, of course, the increasing importance of topology, which has been realized in this last century and has an overriding influence on the large-scale solutions of partial differential equations. That's the one thing which perhaps became most prominent in the 20th century, distinguishes the year 2000 in some sense from the year 1900. So those are the common themes. Now, as a kind of introduction to the problems, at least to several of them in detail, it helps to start with a little bit of background in low dimensions. And here I will just remind you that if you start off in 2 dimensions, the study of surfaces, closed orientable surfaces, then they can be classified, and you have first of all the sphere, and then you have the torus, sphere with one hole, and then you have things with several holes, and the number of holes is the genus, and the unity of mathematics is very nicely illustrated by the fact the same pictures were drawn in John Tate's lecture when he was talking about number theory. So this is a link with his lecture. The genus 0 is the sphere, 1 is the torus, and then we have things of higher genus. And then when you study the geometry of such surfaces, you have to specify what class of functions you want to study. Whether you're studying these surfaces from the point of view of pure topology, where the class of functions continuous functions, or you want to study combinatorial things, piecewise linear structures, or smooth ones, which are differentiable structures. And in the case of dimension 2 at the beginning, all these are essentially equivalent problems. Then you can move on from the real theory into the complex theory, particularly when you have Riemann surfaces. You study things from the point of view of complex analysis. You study holomorphic functions. In particular, if things are algebraic, given by algebraic equations, you relate to algebra. And finally, of course, again going back to John Tate's lecture, you can go into arithmetic, where your equations have polynomial coefficients. This is the class of functions which describe the kind of geometry you're doing, and behind all that, there is the topology picture. The classification of surfaces beyond the topological one, in the case of holomorphic and algebraic curves, there are continuous parameters which are called moduli. This is the kind of historical theory well understood in the 19th century, and the fundamental part of the story are, of course, the cycles which lie on surfaces, the closed cycles that lie on the torus, that go around the 2 axes, and the more cycles in higher genus, and these are formalized by homology theory, and they lead to linear, or what you might call abelian invariance of surfaces. And all of this is, of course, the work goes back to Abel, Jacobi, Riemann, Klein, and so on. This is the great legacy of the 19th century. So that was background. So now let me start with problem 1. I have 4 problems. I have an hour. The minister has now left, so we're not under such pressure. And the first problem is what is known as the Poincare conjecture. So let me remind you about this a little bit. Now we go on from dimension 2 surfaces to dimension 3. This was the first step in the increase of dimension. And again, you look at closed orientable manifolds, not surfaces, but at dimension 3 now. So you look for the 3-dimensional analog of the classification of surfaces in some sense. When you start off with the very first question is, how can you characterize the sphere topologically? And the first condition is you want the sphere, the manifold, to have no homology, no first homology. And the question is that enough to make it a sphere? In the case of the surface, that is true. And in the case of 3 dimensions, Poincaré thought it was true, and he made a mistake. And it's very salutary to remember that even the best mathematicians, the most famous, make mistakes. Usually, they discover the mistake themselves. But nevertheless, you learn a lot by these mistakes. And Poincaré made the mistake. He discovered there was something wrong, and his counterexample led to a new discovery, the fact that you can associate to a manifold the so-called fundamental group, the group you make out of closed paths, where you compose paths into the group by composition, and 2 paths are equivalent under deformation. You get in this way a group, an abstract group, in general non-abelian. So these are not linear invariant, but a non-linear invariant, non-abelian. And the counterexample to the Poincaré's mistake is given by the beautiful example, the fact that the 3-dimensional sphere can be acted on by the famous binary icosahedral group, coming from the symmetries of the icosahedron. That is a group which, when you make it abelian, becomes trivial, so that the first homology is then 0, but the manifold is not topologically a sphere because it has this fundamental group as an invariant. And so Poincaré discovered the fundamental group notion at the same time as realizing his mistake. And then, of course, the refined Poincare conjecture was, if you now make the correct statement, the Poincare conjecture is that if the manifold is not just first homology is 0, but its first homotopy is trivial, it's simply connected, then is that topologically the 3-dimensional sphere? So this is Clay Institute problem number 1 on my list. It dates from 1904, and we just call it as P, not to be confused with P and NP in the previous lecture. Again, you can ask this question in the different classes of functions: topological, just continuous functions, piecewise linear, or differentiable. And it's known, but much harder to prove in dimension 3. These are all the same. So we have one problem, 3 different versions if you like, but the problem is still unsolved. It's been formulated by Poincaré, it's been worked on by many famous mathematicians over this century, and it is still unsolved. There have been many false proofs. Many people have tried, and they've made mistakes. Sometimes they've discovered the mistake themselves. Sometimes their friends have discovered the mistakes. Henry Whitehead was a famous topologist who also made a very subtle mistake, which he discovered and led to some progress too. So that's the first problem. Now, when mathematicians have difficult problems, what do? Well, one thing is you can, of course, offer a large prize, as we've been doing today. Another famous device for mathematicians is you generalize the problem. If you can't solve it, generalize it. But this generalization is, of course, not entirely useless. You hope that by generalizing the problem, you may learn something which eventually will help you to solve the original problem. And very often this process works. So we've shifted now to modern geometry. There is a very famous work of Bill Thurston, which is called the Thurston program. A program is something which is not yet fully completed, but much of it is completed. A lot of work's gone on. It's a big industry. And the Thurston program attempts, in broadly speaking, to go beyond the case of the 3-sphere. If we can't solve the Poincare conjecture for the 3-sphere, the 3-sphere was meant to be the analog of the 2-sphere. But in the case of surfaces, there was this beautiful classification of surfaces according to the genus. And the genus 0 is the sphere, genus 1 is the torus, and genus greater than or equal to 2 are higher genus. And it's well known in two-dimensional geometry, these 3 types are classified according to the kind of curvature they have: positive curvature, zero curvature, negative curvature. And there's a very beautiful classification theory which is important in all sorts of ways. So the Thurston program is an attempt to carry out this much broader program of not just looking at the sphere case, but all, and to try to classify them by the geometries. Of course, the answer is much more complicated, and I can't describe it in detail, but very roughly speaking, the Thurston program hopes to show that every three-dimensional manifold can be built up by some gluing constructions from surfaces, manifolds of constant curvature. And the constant curvatures will be of different types. There are more types now than in the case of dimension 2, but they will include in particular the extreme cases of the spherical ones of positive curvature and the hyperbolic ones of negative curvature. The spherical case, the Thurston program would, if it was solved in general, would include the Poincare conjecture as a very, very special case. But it hasn't yet been solved. Special cases have been solved for the other kinds of geometries, but the sphere is still unsolved. But you can see this Poincare conjecture as really related to a much bigger program which has been generalized by Thurston. The theory of three-dimensional manifolds is also very closely related to the topological theory of knots. Knots in three-dimensional space are very complicated things, as we saw in some of the previous lectures, and it is well known that you can convert problems of knot theory into problems of closed manifolds, and they're essentially the same difficulty. And this is particularly interesting in the case of hyperbolic manifolds. And also mentioned, I think, by Tim Gowers, there was a very famous development in recent years was the invention or discovery by Jones and then by Witten of certain new invariants which can be used to characterize knots. And these ideas came from physics, have had a profound influence, and all of this is part of three-dimensional geometry in a way that is yet unclear what its relationship is to the Thurston program. So there's a lot of activity in three-dimensional geometry going on at the moment. Now, what can we forecast for the future? If I live a problem, what could we expect? Well, these are personal comments. What can we expect? Well, future progress, what could it be? Well, it could come from physics, because physics has led to interesting discoveries in the Jones theory with knots, but this is the kind of physics that is related to particle theory, things like matter, structure, but gravitational theory, general relativity, is more concerned with metric structures, and so you might suspect that the physics of gravitation would somehow lead to insights into the Thurston program of 3 dimensions, and ultimately also to the Poincare conjecture. This is the kind of clue, hint, given by the teacher who can't solve the problem to the student who's trying to solve it. It's my job to give you hints. Now, besides generalizing in the direction of the Thurston program, I want to talk to you about other things that have happened in relationship to the Poincare conjecture over the last century. Geometers have not been idle. So not solving the problem in dimension 3, they also decided to look at problems in higher dimension more than 3. And in particular, if you go up to dimensions at least 5, it turns out that the problem becomes simpler. And the reason for that is that in a manifold of high dimension, there is more room. Well, that's not meant to be a jocular remark. The difficulty with manifolds is partly to do with the fundamental group, which is in dimension 1, and partly manifolds have what's called Poincare duality, which relates the geometry in low dimensions to the geometry in high dimensions. If you've got a manifold of dimension 5 or more, then 1 is a long way from the middle, and therefore the fundamental group does not interact very much with Poincare duality. But in dimensions 3 and 4, the situation is very different. Anyway, in dimensions 5 or more, it was discovered the theory is much simpler, and there are very beautiful results, which I won't go into details, although some things were discovered which are different. For example, the theory of differentiable classification was found to be quite different from the topological classification, and there were beautiful examples, so-called Milnor exotic spheres, of things which are topologically spheres, but are differentiably different. And they are actually interestingly related to the famous icosahedral example of Poincaré, which I've written in there, but I haven't got time to give you details. Those of you who are very quick can read that. In dimension 4, it turned out the situation is much different again. It's different from dimension 5, it's different from dimension 3. But in dimension 4, it was finally proved the topological classification of four-dimensional manifolds was finally achieved by Michael Friedman. Manifolds with fundamental group in dimension trivial, but all the interesting part is then in dimension 2. This is one great achievement, but then almost simultaneously, when this was done and people thought four-dimensional theory was nearly finished, Simon Donaldson discovered that the differentiable theory in dimension 4 was totally different again. There are quite different results. There are manifolds which don't have differentiable structures, and when they do, they're highly non-unique. And there is a whole new theory now of how to classify these different differentiable structures in dimension 4. This four-dimensional theory was a very unexpected development. I would say it was the most unexpected development of recent times. And again, the influence all came from physics. The invariants come from the use of the Anglos Equations, and so subsequently the Seiberg-Witten equations, which I may say more about later. This was a very spectacular result. It applies very particular strong results about the structure of algebraic surfaces, but the four-dimensional differentiable Poincare conjecture is still open. And at this stage, there is no conjectured classification in dimension 4 in sight. Nobody can make a sensible conjecture which offer a prize for. Maybe in the year 2100, the Clay Institute, which is still going strong, will offer that one as a prize. Well, that was problem 1. I've given you a bit about the problem, what was solved, what was not solved, and the importance about a problem, you see, is not just the problem per se, but the influence the problem has on the development of mathematics. And the development of mathematics in this direction was influenced by the Poincare conjecture in the directions I've indicated. A very rich theory evolved. Now I want to move on to problem 2. Problem 2 is to do with what is called the Hodge conjecture. The Hodge conjecture is a conjecture which is on the frontier between geometry and algebra, between algebraic geometry and topology. Now what Hodge, going back to dimension 2, the theory of algebraic curves, the theory of Riemann surfaces, there is a very close relationship between the geometry and the algebra, very beautiful theory. But going above dimension 2, dimension 2 real, if you go to dimension 4, or more generally, even dimension, this corresponds to doing algebraic varieties over the complex numbers whose algebraic dimension is m, whose real dimension is therefore 2m. M equals 1, algebraic curves, m equals 2, or algebraic surfaces, and so on. Algebraic geometers study such objects. And it was a major challenge in the 1930s to extend the classical work of algebraic curves to higher dimensions in a sensible way. And one of the major achievements was due to Hodge. And what Hodge did was not to follow standard algebraic geometry techniques, but to go outside it and to use Riemannian geometry, going back, if you like, to ideas of Riemann in Riemann surface theory, and he applied looking at the Riemannian metric in a manifold, which is the underlying manifold of a complex algebraic variety. He introduced in there the differential operators, the exceeded derivative and adjoint and the Laplace operator, all of which are linear differential operators on a curved background, which are motivated by Maxwell's equations and Laplace's equations. If you like, they are fundamental equations of mathematical physics, put in the geometrical context. He applied these with insight coming from Maxwell's equations, and it led to the beautiful theory that says that the harmonic forms, the solutions of the Laplace equation, the analog of harmonic functions, give you a space which is identified with the homology or cohomology of the manifold. Very beautiful link between topology and analysis on manifolds. And a more precise result, if you have a complex manifold like algebraic ones, which have a particular kind of metric called a Kähler metric, you can refine that decomposition so that harmonic forms can be decomposed into what are called the PQ types, where P and Q refer to the number of complex variables or complex conjugate variables that you involve in the choice of the differential form. This PQ decomposition is a new feature which Hodge introduced. Now, if you take in dimension 2, then P plus Q has dimensions. In the one-dimensional homology, you can only have 1, 0 and 0, 1 types. And the 1, 0 are holomorphic differential forms, the classical integrals of Abel and Jacobi, and 0, 1 are just their complex conjugates, nothing new. When you move on to algebraic surfaces in dimension 4 real dimensions, then if you look at the two forms, you have the 2, 0 forms which are holomorphic, they're complex conjugates which are 0, 2, but you have something new. You have the 1, 1 forms which are mixed. And these are the new things that Hodge introduced, the space of harmonic 1, 1 forms with a new object. At the same time, these things are related to algebraic geometry, because if you have an algebraic curve on the surface, algebraic curve being a two-dimensional subspace of a four-dimensional manifold, you can try to integrate over it the two-dimensional differential forms. And you see the only harmonic forms that can possibly have non-zero periods on such a curve are the ones of type 1, 1, because these have too many complex conjugate variables and these have too many complex conjugate variables. These are the only ones which can pick up the area of the curve. And so algebraic curves have non-zero periods only in this type 1, 1. And so this led Hodge to make his conjecture, which is formally expounded in the Congress in 1950, which is to say that this should be true generally. That if you want to describe here is the fundamental question. You have a manifold, which is underlying algebraic variety. Inside there, you have ordinary topological cycles. But special cycles are those which come from algebraic subvarieties. Those are especially interesting. The question is, which are they? How do you find, amongst all the possible cycles, those which are actually equivalent to algebraic ones? And Hodge's conjecture was, those are precisely the ones which have the right properties with respect to their integral periods of the harmonic forms. So, if you have a cohomology class of dimension 2p, it could represent algebraic subvariety of codimension 2p. You looked at the integrals, and if the only harmonic forms which have non-zero periods on it are the ones in mixed type, pp, then that satisfies the Hodge criterion, and the conjecture is this cycle should be represented by either an algebraic subvariety itself, or at least a linear combination with rational coefficients of algebraic subvarieties. So this is Hodge conjecture. This is problem number 2. What it does, this Hodge conjecture, if you solve it, what it enables you to do basically is to give a construction or an existence theorem proving the existence of algebraic subvarieties of an algebraic variety by transcendental methods. That's a very powerful thing, because exhibiting algebraic things by topological method is a very hard problem. It's very analogous to the sort of thing John Tate was doing in exhibiting rational points on curves, the close analogy. So this is the second problem. Now let me make some comments about what's known, what's not known. Comments. First of all, in one direction, it's easy. If your subvariety is algebraic, then it has the right properties with respect to the periods. The difficulty is to prove the other way around. If it has the right property with the periods, is it algebraic? The existence theorem for algebraic subvarieties is what you're after. Then, of course, you can look at special cases in terms of dimension. And what Hodge proved in particular, the theorem is true for p equals 1, in other words, for two forms, which correspond to divisors, things of algebraic dimension 1 less than the highest. So in particular, for curves on surfaces, it was proved by Hodge. So this is known, but the general conjecture is for all P, things of arbitrary dimension in arbitrary varieties. It's false for integral cohomology. You have to, it's true for integral cohomology in dimension for P equals 1, but in general, that's not true. You have to allow rational coefficients. And a particularly important case for applications is the case when the manifold M is itself the product of two copies of another manifold, also algebraic, let's say X. Because then in that case, algebraic subvarieties on the product of a space with itself are what are classically called correspondences. The graph of a map is a particular case, but a map is one-to-one. A correspondence is many-to-one, and so algebraic subvarieties of products give rise to correspondences, interesting things in algebraic geometry, and if you look at the Kuhn's formula for cohomology, this gives you a very interesting way of characterizing correspondences. The Hodge conjecture would give you that. Now, methods. What methods can one use to try to prove the Hodge theory? Well, Hodge's work was essentially in the 1930s, and then, of course, in the post-war period, in the 1950s, a lot of new methods came into algebraic geometry. There was, of course, the famous development of sheaf cohomology by Leray, Cartan, and Serre. I'm delighted to see here Professor Cartan himself, and this was one of the major contributions, revolutions in algebraic geometry, the systematic development of a powerful machinery applying transcendental methods in global problems in topology and complex analysis. In purely algebraic counterpart of that, there was the work of Grothendieck, which gave algebraic definitions of cohomology, again trying to link the algebraic and the topological methods, and then led to the proof of the Weil conjectures by Deligne, as was mentioned by John Tate. All of this is part of the general big build-up of machinery that took place in this period, providing powerful new tools of a linear kind on a curved background, if you like, which incorporate the Hodge theory is part of the story. It gets absorbed, but this goes much beyond the Hodge theory. But nevertheless, even with all these new techniques, unfortunately, although it solved many classical problems, provided great powerful techniques for machinery, the Hodge conjectures were not solved by these methods. I remember when I was a student of Hodge at the time, when these new methods came in, he was very excited. He told me we should try to solve my old conjecture, and he tried, and other people tried, and it didn't work. So fundamentally, the Hodge conjecture is about bridging the gap between the algebraic and transcendental methods in algebraic geometry. And there is a big gap still, and we don't know the answer. If you prove the Hodge conjecture, the gap will be closed. But who knows? Perhaps the Hodge conjecture is false. I should emphasize that the Clay Institute is very generous. It not only gives you the prize if you prove the result is true, it will give you the result if you prove it is false. But it will not give you any prize if you prove both. In the sense of bridging the gap between algebraic and transcendental methods, the other conjectures, which some of which were referred to by John Tate, Birch-Smith and Dyer conjectures, the work of Andrew Wiles himself, I think fit into this general story of linking transcendental and algebraic methods. And as far as the future is concerned, I don't think I want to make any predictions. All I would like to say is that our knowledge is inadequate. It may well be that there's a much more difficult story. Characterizing algebraic varieties might turn out to be much more difficult than we think. There may be a whole new field to be discovered there, which in years to come will provide a lot of work as future research. So if you think of proving a negative result, you should not think of it as negative, you should think of it opening the door to new possibilities. Well, now I'm going to move on from problem 2 to problem 3, so I'm halfway through. Now, first two problems were problems of pure mathematics. They're problems of geometry, algebra, analysis, and differential equations in the background as well. Problem 3 and 4 are to do with physics. Now, problem 3 is to do with the Yang-Mills theory. So let me try to explain what this problem is and where we are. Now, in 1900, one of Hilbert's problems was essentially to establish the proper foundations of mathematical physics, proper mathematical foundations of physics. That problem is, of course, still with us, if it ever was a well-defined problem. And of course, in 1900, people didn't know about special relativity, or about quantum mechanics, about general relativity, about all the other things that have happened since. So certainly, it was premature in 1900 to think seriously about establishing the proper foundations of physics. The question is the year 2000 a better time? Well, we don't know, but we can try. A lot has been learnt, and if so, at what level? Of course, we don't need to try to have a foundation for everything. We might take the part that we understand well and try to find a foundation for that. So that's the question we want to pose. Well, first of all, let me give you a quick 5-minute review of physics. 5 minutes is fortunate because it's about long enough to cover how much I understand. The review of physics. Well, first of all, we go back to classical physics, Maxwell's equations describing the electromagnetic field, the great theory of the 19th century, which of course underpins all subsequent physics in a long way. Then, of course, after the classical equations of Maxwell's equations, we move on into this century and the discovery of quantum mechanics, and the way particles are treated quantum mechanically is a very different approach, of course, from classical theory. From quantum mechanics, we move on to quantum field theory, where you treat not only particles by quantum methods, but also fields themselves. And in quantum field theory, the notions of particles and forces all get unified in a very mysterious way. So quantum field theory is the theory which combines fields and quantum mechanics. Quantum electrodynamics is the first attempt to unify things together satisfactorily, incorporating also the electromagnetic field and interaction with electrons. And quantum electrodynamics, which was developed in the 1950s, is a remarkable theory. It's a very precise theory, gives magnificent confirmation between experiment and theory to very, very high accuracy. And this theory is given by perturbation expansions, higher and higher order terms in expansion, and there are very complicated rules for how you carry this out. I call these rules because, as a mathematician, I can't call it a theory because there is no well-defined theory. But physicists use the rules, they don't bother with the fact there's no theory, and they get very good answers. And it's very hard to argue with something which gives you a rule for computing something which agrees with experimental results to 10 figures of accuracy. But there is no rigorous mathematical theory, which is an embarrassment for mathematicians. Now, going beyond quantum electrodynamics, we come into the 1950s, where the Yang-Mills equations were introduced. The Yang-Mills equations are, very crudely speaking, a matrix version of Maxwell's equations. You take Maxwell's equations, looked at in the right way, and you generalize them to matrices. And then you get a new set of equations called the Yang-Mills equations, and then you treat all the previous theory with an extra complication. You want to do quantum field theory and so on in this situation, because these equations are meant to describe not just the electromagnetic field, not just those forces, but also the forces that are involved in the small-scale structure of matter, the weak forces and the strong forces. So all the forces involved should be encapsulated in these kind of enlarged Maxwell's equations. The fundamental formula there, which is the one that links the potential with the field, is the one that says F is the differential of A. That would be the formula in the abelian case, but when you have a matrix case, you have a commutator, a bracket, which is nonlinear. That's the Yang-Mills complication, generalizing Maxwell's equations. So the Yang-Mills equations are nonlinear differential equations, whereas Maxwell's equations are linear. And then, of course, you have to build on top all of that, the quantum field theory story. Now, these gauge theories, as they're called, the Yang-Mills are, at present day, the theory accepted by all physicists as the basis for describing structure of matter, all particles and forces, all forces except for gravitation. And QCD, physicists are very good at using short, snappy titles. QED was quantum electrodynamics, in case you didn't know that, and QCD is called quantum chromodynamics, which is to describe the behavior of quarks. Well, that was the quick summary of physics for you. Now, so the problems we're going to concern with now is how to develop a quantum field theory based on Yang-Mills equations. And this is a nonlinear equation, much more difficult than quantum electrodynamics. But of course, even quantum electrodynamics we didn't know how to treat, so you might think this is worse. If we couldn't solve the easy case, how can we solve the harder case? Well, there are reasons to make you believe this is a better theory. There are some good features of Yang-Mills theory which are not present in the simpler case. There is what's called asymptotic freedom, which tells you about what happens in the very, very small scale regions. There are also what's called renormalizability, fundamental properties to do with scale changing. And these are features of the Yang-Mills theory which are not present in the linear theories. In some sense, the linear theory is too naive. So this gives you some hope that this theory will behave better. Now, before going on to describe the problem, let me digress a moment. One of the remarkable things, and this I know more about than the physics, over the last 25 years, has been the impact on mathematics of these new ideas in physics, the Anglos Equations, the gauge theories, and so on. This impact of physics on mathematics has been truly one of the most remarkable developments of the past 25 years. It's had an enormous range of applications, examples in geometry, topology, algebra, in a whole range of areas. I mentioned just a few. The invariance of knots I mentioned of Vaughan-Jones came out of this story. So did the four-dimensional theory of Donaldson, also comes out of this story. So did what are called quantum groups evolved from here, used very much by group theorists, and I mean real group theories, people who do things in characteristic P and things like that, finite groups. Quantum cohomology is a new notion which emerged, obviously, from the terminology, some kind of hybrid between cohomology theory and quantum ideas, and it has a very important application to very classical questions such as the counting of curves in algebraic geometry. These are a vast range of new ideas have come in with fantastic consequences into mathematics. So, as a mathematician, I'm very interested in these ideas of physics coming in. One of the drawbacks of using a physical idea is that physics is not rigorously proved, so all the ideas you get come to you incomplete, and therefore the mathematician has to work hard to find some kind of proof of the result that is motivated by the physics, and there's a big industry. One of the biggest industries of the last 20 years is trying to make mathematical proofs of what comes out of the physics. Of course, if you could prove the physics was rigorous, then you would save yourself a lot of work, because all this mathematics would be rigorous too. In some sense, that's part of the motivation here. So the problem 3 of the Clay Institute list is essentially to establish Yang-Mills theory as a rigorous quantum field theory. Now, I don't no time to go into the technicalities of what this means, but the important thing is to show what's called the existence of a positive mass gap, that the Hamiltonian of this theory, its first eigenvalue, should be strictly positive. This is meant to be true. Physicists believe it. The question is to establish a rigorous foundation of the theory with this as a consequence. Of course, this then would be provide mathematical basis for the real physics of the world. It would also, en passant, provide justification for all the beautiful applications to mathematics. So both physicists and mathematicians would like to know whether this can be done. This is the problem. Now, this is, of course, a very difficult problem because it has to do with infinite dimensional analysis, because you're dealing with quantum field theory. It involves analysis and certainly a lot of topology and algebra, because these spaces are very complicated, and this is, I would think, the hardest of the problems that the Clay Institute has put forward. In some sense, the most recent. The Anglos equations go back to the 1950s, but these attempts to do this are more recent still. Now, I should say a word or two about rigorous attempts to quantum field theory in general. This goes back to the work of Arthur Weightman, who laid down an axiomatic approach. What is a quantum field theory mathematically? What should it mean? He drew up a list of axioms which are plausible, what you would mean, and then the question is, can you actually construct mathematical objects that satisfy these axioms that will be the physical models that you want? And that program was then carried out to a considerable extent by Arthur Jaffe and his colleague Glim in dimensions 2 and 3. First in dimension 2, and then with enormous efforts in dimension 3, but certainly it stopped short of dimension 4. And as we know from geometry and other contexts, these changes in dimension are by no means trivial. You don't just add 1 and carry on. Enormous new phenomena happen. Things are quite different. The equations in dimension 4, for example, are conformally invariant. They're not so in dimension 3 and 2. So the change from dimension 3 to 4 is profound, and therefore we don't at all know how to carry that out. So that's really the big dimension 4 is a very special dimension, and the work of Simon Donaldson I mentioned in pure geometry, which emerges out of the physics, is an indication, because the things that were discovered there are unique to dimension 4. Well, what is the future of this problem in physics? What could happen? Well, this is now my personal guess, or if you like, hints, suggestions. Well, you can try a direct analytical assault. If you're a young man and brave, and you have looking a long way into the future, you can just get out your hammer and chisel and crack away. First you read Dim and Jaffe, and then you start on dimensional 4. Or you might think you want something different. You might find this is basically get a better understanding of the formal structure of quantum field theories of this Yang-Mills type. These Yang-Mills theories have a very elaborate mathematical formal structure, which incorporates very mysterious dualities of various kinds. It involves also things called supersymmetry, and many of the applications to mathematics incorporate all these. So here there is a very elaborate structure, and it is just possible that if we get a better understanding of that structure, then that might give us a better way of trying to lay the foundations. For example, a problem that can be described in two different ways by a duality. The two dual pictures might look quite different. One of them might be tractable, and the other one might be intractable. And so there are certainly not at all unreasonable to think this might give you a way of starting if you understand better these formal apparatus. The formal apparatus here is very sophisticated. You could, of course, sit back and wait. Await development in string theory. String theory and the latest things that follow string theory, called M theory, and every year there's a new theory, develop at an enormous rate. The theoretical physics community here is tremendously active. There are very beautiful things happening every week. New results come out. Many of them will have mathematical overtones, and it could be that if we wait a few years, there will be such a totally new picture emerging from string theory that we'll get a better idea how to go about tackling the problem. So that's not an unreasonable expectation. You see, trying to lay the foundations for physics is like an architect trying to lay the foundation for a building that's rapidly going up. I mean, which do you do first? It's not quite clear. Do you want to see the design, or do you want to lay the foundations? Maybe we want the design first. Then, of course, you might also sit back and say, well, quantum electrodynamics was very hard because we didn't incorporate extra things like protons and neutrons. We only worry about electrons. Maybe even that isn't enough. Perhaps we should incorporate gravity, and then we'll have all the forces under control. Perhaps at that stage, the fundamental theory will be even easier. And people in string theory aim here, and this is the ultimate theory, and perhaps the ultimate theory will be easier than the transitional theories. But who knows? And the big challenge for mathematicians and physicists of the 21st century is to say, really, to make progress along this program by whatever method they can. Good luck to you. I haven't finished yet. Unlike John Tate, I have 4 problems. The fourth problem is also in mathematical physics, but of a much more traditional kind. This is what's called the Navier-Stokes equations. Navier-Stokes equations. Now, the Navier-Stokes equations are the partial differential equations that describe the flow of a fluid which is incompressible but viscous. Incompressible viscous flow and the equations which describe this are very well established. They go back for 100 years, Navier and Stokes from the 19th century. They're widely used in practice. You fly on an aeroplane or you go on a boat, you thank your God that we have the Navier-Stokes equations. And they have a wide range of validity. Of course, every physical model is an approximation, but it's a pretty good approximation for most practical purposes. And it has very great practical importance, even though the mathematical theory of the Navier-Stokes equation is incomplete. It doesn't stop people using it and getting practical results. So there's a great deal of practical work going on in getting numerical results of the Navier-Stokes equations. Now, what are the equations? First, well, the equations they describe the velocity of a function, vector function ui of x and t. X is a coordinate in space. Space here is 3-dimensional, and time is a positive number evolving from given time 0. These functions ux of t. There's also pressure, a scalar function p of x and t, and they are subjected to the 2 differential equations that are the Navier-Stokes equations. The first equation essentially involves the partial derivative of u and the nonlinear term here involving the product of u and the derivative of u. And there is a viscosity term, a coefficient nu in front of the Laplacian of ui, there is the gradient of pressure, and then there is an unknown given external field, which you may say could be 0, but could be, for example, given by the gravitational field if you're studying water moving on the Earth. And then there is the divergence equal to 0 of u, which is the incompressibility of the flow. These two equations are easily deduced from fundamental principles of Newtonian mechanics, describe fluid flow of an incompressible but viscous flow where nu is the viscosity, is positive number. Then you put, of course, boundary conditions that the fact should vanish on the boundary, and you can either take a finite boundary, or you can take the whole space, or you can do a periodic problem if you want to put it on a torus. All these are variants of the boundary condition. And then you put initial conditions at time 0, you give the data. The data is some function nu 0 of x which is prescribed. Standard equations of evolution equations in mathematical physics, hyperbolic system of equations, initial data, study it in forward time under suitable boundary conditions with suitable initial values. Typical problem of mathematical physics, and the question is, Navier-Stokes problem is to prove or disprove the existence of smooth solutions for all time under reasonable assumptions on the initial data and on the external field. Reasonable assumption would mean obviously smoothness of the data, suitable decay if you're in the whole space, and so on. I won't go into the technicalities. Question is, given reasonable conditions, boundary conditions or initial data, prove the existence of solutions for all time, all time. Smooth solutions remaining smooth for all time. That's the problem. Is that true? Can you prove it? And if you can, you come along to Mr. Clay or Mr. Arthur Jaffe or whoever is there in that place in 50 years' time, and you ask for your prize. Well, what are the comments? What do we know? What do we know? Well, we know, first of all, you can do these Navier-Stokes equations in dimensions 2 or 3. In dimension 2, things are much simpler and things have been proved. Dimension 3 is where things get hard. There's a big difference between dimension 2 and 3 for this problem. It's also proved for small time. If you give the initial data, then you can show that there is a solution for small time. Things will evolve for a short while. Nothing will go wrong. You can also prove that the solution will go on for a long time if the initial data itself is small. If you get a very, very small disturbance, then the thing will propagate for a long time, and the length of the time will be some function depending on the size of the data. You can estimate that. But that's not the same thing as all time. There is also a very important fundamental result proved by Leray in 1934, which proves that there are weak solutions. Now, weak solutions are generalized solutions, related to Schwarz's distributions. You integrate average things and study the average behavior. And these have been proved to exist for all time. But a weak solution, of course, is not the same thing as a real solution. It can hide lots of singularities that develop. And the question really is, do those singularities develop or not? So now, there are some partial results. So once you've got a weak solution, this is one of the standard techniques of partial differential equations, is to take a weak solution and then study it afterwards and subsequently show that it really is in fact smooth. These are called regularity theorems. And some partial results on regularity of weak solutions have been proved. You can give some kind of estimates on the nature of the singularity if it's there. But that's a long way from saying there are no singularities at all. So this does not solve the problem. It's a step in that direction. And moreover, the analytical techniques that have been used so far seem as though they've reached the end of their possibilities. Standard techniques of analysis on this kind of problem are not going to give rise to the global solution. It doesn't seem you'll need new ideas to solve the problem. Now, do we expect a positive answer or a negative answer? Well, if there's a negative answer, that means that there will be some solutions that can blow up in finite time. Finite blow up will mean that something will become infinite. Of course, physically, what that means is that your model is no longer valid in that regime. Every model has its limitations, and if the mathematical solution goes outside those limitations, it's no longer applicable. It doesn't mean the physical world doesn't exist, of course. The physical world is there, your mathematical model may be inadequate. So the question is, is the Navier-Stokes equation a sufficiently good model that remains for all time a good approximation? It's not guaranteed. You see, you must not make the mistake of assuming that the physical world is constrained by our requirements. So it's another error mathematicians make. Now, numerical calculations can be made, of course, a big way, and there are some numerical indications that singularities can develop. But because the equations are nonlinear and numerical calculations go on for a long time, it's very unclear whether those blow-ups that come from numerical calculations are really blow-ups or they are simply a result of the numerical approximation. It's unclear. So, indications, but not more. Now, one of the important things in fluid mechanics is the so-called vorticity. The vorticity is given by the curl of the velocity vector, and when you introduce the equation for the vorticity, the pressure drops out. You get a new differential equation just for the vorticity alone. And vortices are very interesting things in fluid mechanics, as you know, and they have a lot of topological properties. And in fact, it may turn out that the topology of vortices may explain a possible blowout progress. I've been talking with some of my friends in fluid mechanics who say there are ideas about possibly in which ways certain vortices might develop and crystal around themselves. That would explain a possible blowout process. So these equations are nonlinear. Nonlinear equations, as I said, hide inside them some possible topological effects which are related to vorticities. And treating a differential equation purely as a piece of analysis or algebra, it can ignore some fundamental reality of those equations which may be topological and may reflect some physical phenomena. So keep an open mind. It may well be there's something happening in the physical world which we don't yet understand. Numerical calculations may suggest it. It may be that you should try and disprove the conjecture. But of course, that's also hard. And if this process happens, it will have a significance for turbulence and so on. Now, let me make a remark here. This will link up with other things. And that is that in 1869, Lord Kelvin put forward a theory of what are called vortex atoms. Because hydrodynamics was well developed at the time, atomic theory did not exist, he put forward the theory that atoms are really knotted tubes of the ether. You thought of the fluid, some sort of ether, some kind of fluid, thought of vortices in that, you thought of vortex becoming some kind of knot, and the idea was that atom was some kind of vortex, knotted vortex tube. And this stimulated the whole development of knot theory, the famous Tate conjectures, Tate, T-A-I-T, not John Tate, which were only solved 100 years later by Vaughan-Jones using the ideas coming out of mathematical physics. So you see an interesting link here between the ideas of vortices and fluid mechanics, things coming out of quantum field theory, geometrical applications, all of which I think help to strengthen one's belief in the fundamental unity of mathematics. But of course, as a solution of this problem, we don't know the answer, whether it's going to be positive or negative. Let me just finish with a brief remark about the Euler equations. The Euler equations are what you get if you take no viscosity. The equations are therefore simpler than the Navier-Stokes equations because one term drops out. This is sometimes called an ideal fluid. But in fact, this equation is analytically more difficult than the Navier-Stokes equations because the nonlinear term, the second derivative term, which you've dropped out, helps you to control. So the equations are easier in some formal sense, they are more difficult analytically. But geometrically they're easier to understand, and for example, Arnold has interpreted the Euler equations as a Hamiltonian flow in an infinite dimensional space and related to nice things in topology. So you can say quite a lot about these simple equations, but these are not the equations for which you get the Clay Prize, but they're interesting equations nevertheless, and some interesting comparison between different classes of equations you get by using different models. Well, thank you for the extra time the minister gave me by coming in the middle, otherwise I was going to be compressed. But these four problems, I think, give you a range of the spread of things in mathematics, including important areas of mathematical physics. But at the same time, I have tried to emphasize there are some overarching possible unifying ideas, and you shouldn't think that you can apply a particular set of tools to a problem. You should come in open-minded, look for all ideas, all sources. And if you're working in an area which is at all related to mathematical physics, it's very important to talk to the physicists, to talk to the people outside, because the ideas coming from there can give you surprising input into the mathematics itself. So I think with those final remarks, I'll close. Thank you.
On behalf of the Clay Institute, I'd like to thank all the people who participated in today's session. I'd like to invite you to a champagne and some hors d'oeuvres outside, and also to say if this evening you solve one of the problems, send it to a journal. Don't send it to us, but in 2 years we'll consider it for the prize, and each prize is $1 million.